Hello. In this screencast, I'm going to summarize some of the results from the lab that we did and turn them into some usable force laws that we'll use to describe friction. And I'm also going to distinguish between kinetic friction, which is the type of friction that occurs when two objects are actively sliding across each other, as we did in the lab, as opposed to static friction, that is to say, friction between two objects that are in contact but not sliding across each other. Today we had our quiz, we finished the friction lab. I'm going to codify friction now, and there is a 2-problem WebAssign homework due tomorrow. All right. Let's first talk about why friction happens in the first place. If you zoom in to the molecular level of the interface between two surfaces, they're kind of jaggedy. They're not perfectly smooth. Depending on the materials, they'll be more or less jaggedy. There are imperfections, and when you imagine dragging these surfaces that are jaggedy and bumpy and imperfect across each other, then you can imagine that the bumps press into each other and they resist that sort of tangential sliding across one another. That's what friction comes from. We found that it's not just the mass of something that affects whether there's more or less friction, but how much pressing it is doing into the surface it's contacting. For example, when you move your hands lightly across each other, there's very little friction between them, but when you press into each other, you're increasing the normal force between them, and that consequently increases the friction force between them as well. So there's a small normal force when the surfaces are just lightly grazing across each other. But when there's a large normal force between two surfaces, you get more resistance, more friction force. And so when the groups varied the amount of mass blocks on the sledge, what they were really varying was the amount of normal force between the table and the friction sledge. Those groups got roughly this graph. Here I'm graphing normal force on the horizontal axis and friction force on the vertical axis. Kinetic friction, moving friction, sliding friction, behaves a little bit like this. When you increase the normal force between two surfaces, you increase the frictional force between them as well, and it obeys a roughly linear relationship. 0, 0 is a point because if you imagine two surfaces that are approaching, not touching at all, approaching no normal force, they will have very little friction between them as well. So let's talk about what this coefficient is. I've called it mu. That's the Greek letter mu. Check it out. I write it like this. You might pause the video and practice writing mu a couple of times. It will be our friend in this class. Mu, the coefficient of friction. And I have a little subscript k there to indicate kinetic friction because we're talking about sliding. The force of kinetic friction is equal to the coefficient of kinetic friction times the normal force between two surfaces. So what are the units of this coefficient, of this slope? Well, it's the units of the vertical divided by the units of the horizontal. That's newtons per newton. That's unitless. So what is this mu? It is what I'll call the coefficient of friction, and it tells you how many newtons of frictional force there are per newton of normal force. I'll say that again. It tells you how many newtons there are of friction force per newton of normal force. It has units of newtons per newton. It is sometimes known as the friction fraction. And what is it a property of? The coefficient of friction is a property of an object, a surface. Well, there was one group that varied the interface that they were sliding the sled across. They tried sliding PVC on whiteboard and PVC on table and styrofoam on whiteboard and styrofoam on table. So there was a different amount of friction force that they encountered for each set of materials, a different coefficient of friction for each interface. I'll say that the coefficient of friction is a property of an interface, a property of two materials. Here's a little chart showing coefficients of friction for different pairs of materials, different interfaces, and you can see as a preview that the coefficient of sliding friction or kinetic friction is different than the coefficient of static friction. We'll talk about that in the next slide. The direction of kinetic friction is always, the direction of a kinetic friction force is always, let's see, what direction is the force of the ice, which doesn't exert that much friction, but it exerts a little friction on this polar bear? I think it exerts a force opposite the bear's motion. The direction of a kinetic friction force is always opposite to the velocity that an object is sliding. Here are some things that, perhaps surprisingly, the force of kinetic friction does not depend on. It does not depend on the amount of surface area of contact between two surfaces. Why is that? Well, you might imagine that if there's a larger surface of contact, there would be more friction force because there's more contacting. However, you might also imagine that if there's more surface area of contact, there'd be less friction because the pressure involved with pressing these two imperfect surfaces together is less. Those effects cancel, leaving a kinetic friction force that approximately does not depend on the surface area of contact. It doesn't depend on velocity. Whether two objects are sliding across each other very rapidly or very slowly, they still have the same coefficient of friction, and they have the same friction force for the same amount of normal force. There is a slight dependency of coefficient of friction on temperature, but usually that's not going to come into play during our problems. So now that we have a force law for kinetic or sliding friction, I'd like to talk about static friction. That is to say, this person is pressing against this car here, but I doubt very much that he's succeeding in moving it, because I happen to know that the car has the parking brake on. More simply, you can imagine that I had a brick here on the table as I represented here. And then you can imagine that I'm just taking my finger and pressing with a 1 Newton applied force with my finger to the right. You can imagine that that's not quite sufficient to move the brick. The brick stays put on the table. Why is that? Well, it's because there's a friction force opposing my applied force, the friction force to the left. And this is not a kinetic friction force because I've specified that I haven't yet pressed hard enough to get the block going. You could imagine that maybe I'd even press harder on the block with a 2 Newton applied force to the right, but that still might not be enough to overcome the friction force and get the brick moving. So I guess in this picture, the amount of friction force between the brick and the table is 0. But in this picture, the amount of friction force between the brick and the table is 1 Newton to the left. Here, the amount of friction force between the brick and the table is 2 Newtons to the left. So it looks like when an object's not moving, not sliding across another surface, the value of the friction force can take on many values. The friction force can be 0, or 1 Newton, or 2 Newtons, or 1.5, or 1.2385959. There are many different values that the friction force can take on when it is a static friction force. And it takes on different values in a way that is kind of like that of a reaction force. The friction force sort of depends in part on what applied force I'm putting on this brick. However, you can also imagine that there's only so hard I can press on this brick before it will actually start accelerating, before I overcome the friction force and succeed in accelerating that brick to the right. There's a maximum amount of static friction force. What factors might affect that maximum value of static friction force that occurs right before I succeed in starting to move it? Well, the same things that might have affected the kinetic friction force in the previous slide. Turns out that the maximum value of the static friction force does not depend on surface area. It depends on the amount of normal force, the amount of pressing that the brick is doing into the table in this example. And it also depends on the coefficient of friction between the interface and how bumpy these two surfaces are into each other. How imperfect. In other words, the maximum static friction force, the force of friction, static, maximum, the maximum value of the static friction force depends on the strength of the normal force between two objects and also on something having to do with their interface. Here's our force law for static friction. Static friction force can be as little as 0 newtons and as much as some maximum value given by the coefficient of static friction times the normal force between the two objects. The direction of a static friction force is always, and this is a little tricky, it's always opposite to the velocity that an object would have if there were no static friction force. So let's just think about that with a concrete example. With this brick, I apply a force with my finger to the right. What direction is the static friction force acting? To the left. Opposite to the acceleration, the velocity that the brick would have if there were no static friction force. I'd like to close by comparing the kinetic and the static frictions comparing the static and kinetic coefficients of friction for a given interface. If I have my brick on the table, you might wonder, is the coefficient of kinetic friction the same as the coefficient of static friction, greater than, less than? There will be a demo that I do in class the next time we meet that shows that, in fact, the coefficient of static friction exceeds the coefficient of kinetic friction, and this is true for any interface. In other words, it takes a little bit more force to get something moving, to overcome static friction, than to keep it moving, than to overcome kinetic friction. That's what I want to say about that.